If you, for example, you choose 14 or 21, you still have to divide. We don't have enough tools right now to find antiderivatives of all functions, and we're not going to even have them in the course for all functions. Okay, let's move on to the second type of problem. Let's start with the 32, and please choose the next one if you'd like. So this is the second situation. In 32, we are given f prime. We are told that is 5x to the fourth minus 3x squared plus 4. And we are given a condition. This time we are no longer asked to find the most general antiderivative. We're asked to find the specific function, specific antiderivative, whose derivative is this, but also fulfills this condition. Okay then, so I have, the notation is f prime, I have to use f of x. When the notation is lowercase f, I use uppercase f. When the notation is f prime, I have to go back to f. I keep 5 in front. I increase the power of 4 to 5, and I divide by that number. I keep -3. I increase the power to 3 and divide by 3. Which function prime is 4? Obviously is 4x, plus a constant c. I will be able to find c from the given condition. So that's why the answer will be unique. I will clean this up and write f of x equals x to the fifth minus x cubed plus 4x plus c. And I'm told that f of -1 is 2. This is the condition specifically given for c. So -1, -1 to the fifth. -1 to the third is -1 with 1 in front is positive. This is -4 plus c equals 2. These two go away, so c is 6. So therefore, there is only one function, which is x to the fifth minus x to the third plus 4x plus 6. That fulfills the given conditions. There is nothing else. Any questions? Any questions? Any questions? Okay, let's choose another. I would like to look at an application of what I just said with velocity, acceleration, etc. And then we'll come back to more examples of regular ones, the abstract ones. Let's look at 62, page 349. We are given the acceleration of function as a function of t, 3 cosine t minus 2 sine t. And we are told that s of 0 is 0 and v of 0 is 4. A particle is moving with the given data. Find the position of the particle. Okay. I am given the second derivative. I'm asked to find the function. I cannot jump from the second derivative directly to the function. I have to find the first derivative first. I have to find the velocity first. So then the velocity is the antiderivative of the acceleration. So let's see what we write. 3 is 3. Which function prime is cosine? Well, that is sine. Which function prime is sign with minus in front, so it's positive 2 cosine t plus a constant c. I'm going to call it c1. You'll see in a moment why. Let's check. 3 sine t prime is 3 cosine t. Positive 2 cosine t prime is negative 2 sine t. C1 prime is a constant, is 0. I am given this piece of information in which I'm told that v of 0 is 4. Okay. So when I plug in 0, 3 times sine 0 plus 2 cosine 0 plus c1, I get 4. But this is 0. Cosine 0 is 1. So 2 plus c1 equals 4 gives us c1 equals 2. At this point, I can say I determined the unique velocity function. There is no other v of t, but 3 sine t plus 2 cosine t plus 2. This is the velocity. However, this is not what I'm asked to find. I'm asked to find the distance. So I'm given the first derivative. Now I have to go back to the function. So that would be s of t, which function prime is 3 sine t, and that is negative 3 cosine t. Because when I differentiate negative 3 cosine t, I get sine t. Plus 2, which function prime is cosine? Well, it's sine t. Plus, which function prime is 2? That must be 2t. Plus a constant c2 to be differentiated from c1. Not to be confused with c1. Okay, I am given another piece of information. I am told that s of 0 is 0. That will help us determine c2. So s of 0 is 0. So negative 3 cosine 0 plus 2 sine 0 plus 2 times 0 plus c2 equals 0. This is 0, this is 0, and this is 1, so negative 3 plus c2 equals 0, c2 equals 3. I finally determined the distance function of the particle. Negative 3 cosine t plus 2 sine t plus 2t plus 3. And this is not a family of functions. This is the unique distance formula that verifies the given conditions. That the acceleration is this is a condition, and this is the second condition given to us. Any questions, please? Any questions? I would like to look at one more problem and then continue. Unless you want more, I'm sure you may decide otherwise, and I will comply. 4 plus 6x plus 24 x squared. But this time I'm given f of 0 is 3, and f of 1 is 10. And again, I'm asked to find the specific function. Any questions? How do we proceed? I'm given the second derivative, so the notation, first of all, since it's the second derivative, I have to write f prime. When I'm given the function, I have to write the uppercase. But here I have to write f prime. I'm going to start in the correct order. So 24 x to the third over 3 plus 6 x squared over 2 plus 4x plus c1. I will clean it up, simplify. So this will be 3x squared plus 4x plus c1. I do not have any information. I'm not given a condition or a boundary condition, it's called, for f prime. So I have to continue. Now I finally reach the function. So f of x, 8x to the fourth over 4 plus 3x to the third over 3 plus 4x squared over 2, careful now, plus c1x plus c2. The derivative of this is this, 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 the derivative of this is 0. I will clean it up as 2x to the fourth plus x to the third plus 2x squared plus c1x and plus c2. I see I have two variables, but I am given two conditions. I'm given f of 0 is 3 and f of 1 is 10. So f of 0 is 3 means 0, 0, 0, 0, c is 3. c2 is 3. I will rewrite the function. So f of x then is 2x to the fourth plus x cubed plus 2x squared plus c1x plus 3. And now I will use the second condition, f of 1 is 10. So f of 1 is 10 means 2 plus 1 plus 2 plus c1 plus 3 equals 10. So 2 plus 1 plus 2 plus c1 plus 3 equals 10. So this is 7. So 5, 6, what is it? So I do have 5 plus 3, 7. So subtracted from 10 is 3. Sorry. So I have 8, sorry. Subtracted from 10 is 2. So now we finally have the unique function, 2x to the fourth plus x cubed plus 2x squared plus 2x and plus 3. This is the only function, not a family of functions. It's the only function that fulfills the given conditions. Any questions for me? Any questions? Any questions? Do we need more examples? Let me know if we can move on. Do we need more examples of any kind?
You kind of mentioned it earlier.
Yes.
That, if, you know, I guess I can kind of understand why these would be useful if, you know, an object, for example, velocity, but you need to know, I guess, its position at a
yes.
time.
So yes, if you're given the acceleration, you may want to find the distance. You may want to find the velocity. So your question is, where will this be useful?
Right.
Excellent question. Very good. Here's an example. Unfortunately, we are not going to get to this. This is in Calc 2. I love this part of Calc 2. So let's suppose I have a function. And it crosses at 0, let's say, and 1. So it's x minus 1, so this is x squared minus x. It's a quadratic function. And let's suppose I want to rotate this piece around this line. Let's say -2. So here's what's going to happen. So this is distance of 2. I have to have a distance of 2 here. So I'm rotating this piece around this axis. So let me see. It's a very good question. I love to answer this. So I'm just going to create something. I don't know if I have my pair of scissors here handy, because I don't want you to wait. I think I do. I got it. So I have that little piece of an area, so I'm just going to just create something similar so I can explain easier. It's a very good question. So imagine that this is my piece and I want to rotate it along this axis. So here's the axis and here's my piece, and I rotate it. And by rotating this area around this axis, I create this solid that is empty inside, right? So it's empty inside. The cylinder is void, right? But then I still have this volume. How do I determine this volume? Everything is based on antiderivatives. So in order to determine the volume, I would have to find the volume equals with finding an integral. Finding an integral is nothing else but finding antiderivatives. And there is a very interesting mechanism, quite simple. We're going to cut this with, imagine a loaf of bread. So let's say this is a loaf of bread and I cut it in slices. So we're just going to cut and we're going to create a particular slice, and then we're going to integrate from 0 to 1 and get the result. But everything is based on antiderivatives. We will not be able to determine the volume, or in other situations, we may only be interested in determining this area, which we are going to do in the next chapter. We're going to find this area. Well, in order to find the area, I have to find an antiderivative. Without finding the antiderivative, I will not be able to find the area under the graph, let's say between 0 and 4. So the area will be given by the antiderivative. So tons of applications. Determining a distance or an arc length. So these are wonderful applications, however, not in this course, in the next one. Volumes by cylindrical shells. Without knowing how to integrate, we're not going to be able to find the volume, or without knowing how to find the antiderivative. So these are volumes. Also areas. Areas between curves. Again, this is in chapter 6. I would love to show you this, but this is in chapter 6. These are applications of antiderivatives. All of it. And after chapter 6, I was just mentioning to you, you're going to have the techniques of integration. Integration by parts, substitution, trig substitution. So everything is based on integration, which is an antiderivative. Very good question, Brian. Thank you. So yes, everything is based on antiderivatives, which will, in chapter 5, we're not going to use this name anymore that much. We're going to use integration. Okay, very good. Thank you.
Yeah, thank you.
And we are going to see how this works right now. Any more questions, or we start chapter 5?